Hello everyone, we are Team Zebra and our project is a continuation from last year's project, Printer Real-Time Torque Measurement. Our technical director is Matthew Corviz, a URI Mechanical Engineering alumni who graduated with a bachelor's in 2008 and got his master's in 2016. This year we have a team of three. We got me, Kevin Suggs, we got Dean Grupposo, and Roy Oza. I'm the team's computer engineer and will be a part of the class of 2023. Dean and Roy are the team's electrical engineers, but Dean will be in the same class as me, 2023, and Roy will be a part of the class of 2022. Alright, so let's talk about Zebra. Zebra Technologies is located in Lincoln, Rhode Island, but have many other locations around the world. The company was established in 1969 and is the market leader in mobile printing technology, but is also the industry leader in areas such as barcode scanning and specialty printing. So the motivation behind this project is very similar to last year's, but with some added stuff to it. So first and foremost, we want to continue to improve the fixture design by interfacing the transducer, interfacing all peripherals to one device, and taking that device and putting it on a printed circuit board. In addition, we want to try to implement a GUI, or graphical user interface, to handle the operations of the device and gather and output data to the user. The best outcome of this is first interfacing the transducer by gathering signal data from it and connecting it to the GUI. Second, having ease of test, which will give us a user-friendly interface and faster troubleshooting. And third, having it be versatile so it can be applied to all or many printers. Some of the team's accomplishments on the software side of things include the development of the GUI. The GUI can currently do background calculations as well as serial communications by sending and receiving data. And while we're talking about serial communications, we're doing that by using the Python script and C, as well as PuTTY so we can confirm the communication between the microcontroller and the Python script. On the hardware side of things, we've been working with the dev bench by fixing and optimizing last year's code, as well as checking the functionality of the driver board. As for the transducer, we've been gathering signal data to be sent to the GUI and making a filter to accommodate the transducer's waveforms. The success of this project will have an economic impact on the company because it will give it much more reliable data collection, and because of that, it will reduce costs by lowering budgeting towards troubleshooting and reduce risks of malfunction. Now this is our simple block diagram, which shows us how exactly the fixture operates, but there's something missing. Ah, yes, it's the GUI. The GUI should be connected to the microcontroller as it will send and receive serial data from it. So now let's see what I contributed to the GUI. So let me tell you what I did with the GUI so far. So the GUI is coded in Python and is made using tkinter, and currently it can pass variables via the serial port to the microcontroller. Now the microcontroller uses its own IDE called STM32Cube IDE, which codes in languages C and C++. And for the most part, I've been working with serial communications by passing data between the microcontroller and the GUI. So this right here is our current GUI. And yes, there's not much to look at and it's very basic, but it gets the job done. And in future, we want to improve its functionality by giving it an output display. And this display will be a graph using data points from the transducer. That little open button right there will eventually open Excel files and fill in the data points automatically. And then obviously we want to improve the appearance of the GUI and make it look a lot more pretty and less basic. So now I want to pass it off to the next designer, Roy Oza.
Thank you, Kevin. So this block diagram here relates back to the low-pass filter I am doing as we want it to send a signal to the microcontroller with the GPIO, as we're going to hook it up with the printer and hybrid stepper motor. It goes through the microcontroller and the goal is that it receives the signal so it could work when we fuse everything with the transducer. So as we go to the next slide, my main feature or job in this process is that I'm supposed to design a high-pass filter and a low-pass filter. I had to research what it was, what the size of the components, and how we got it. At first, I made it on multisim so we knew the circuit would work. But as we thought about more about the project, we wanted to switch from high-pass filter to low-pass filter because as we did more research, we concluded that we don't want to capture the fast, instantaneous spikes of the torque, and those were carried over the existing fixture. This was related to our motor tester, and the higher frequency torque spikes don't result in stalls because they are so fast we want to filter them out. I also organized a pinout of the nuclear board in DRV8424 as the code from last year was out of order and we needed to write a new pinout legend so we could use it with the transducer. As I go to my next slide, my accomplishments for next semester will be how to use the low pass filter with the transducer and how signals of the transducer will help printing labels. I will also assist in the code from the STM32 that will help printing labels easier and help connect the software to the hardware. Now I will hand it off to my partner Dean.
Thank you, Roy. Now, returning to the block diagram. While my partner Kevin has been working on the GUI to send data back and forth between software and hardware, and Roy has been working on the filter to make the transducer signal more readable, I have been working with the development bench itself, working on integrating all of the parts necessary to read signals from the transducer while the printer is active. This would be best represented by the arrows between each device in this diagram. So, moving to my contributions, my primary focus was on the microcontroller. My first steps were going back through the previous team's work and fixing some errors that were preventing the system from working properly. This included an arithmetic error, where the printer DPI was off by a factor of 2 within the code, and an error with high Z inputs that required changing some components on the stepper motor driver. After fixing these problems and getting each microstepping mode to work, I moved on to bringing the T25 transducer into the system by soldering wires to a connector and learning which wires I needed to read the signal. Then I began to work on the ADC, which is used to turn this signal into data that can be graphed later. I used many methods to interpret the signal, and I used function generators and oscilloscopes to test my setup. I also created a voltage divider to limit the peaks of the signal and to make it more reasonable for the microcontroller to interpret. My future contribution will involve more than what I have done so far, namely taking the signal data and graphing it. I'll be working with Kevin in the future in order to combine our two tasks, enabling a user to enter data in, process it, and print out a label, and then take the data coming out of the transducer and overlay a graph on top, as you can see to the right here. Eventually, once this is all working, I'll move on to making the system more modular by allowing for different printers to be set up and measured, and exchanging the printer for what is called a particle break to test motor torque in a different way. Now that my team and I have discussed all of our technical contributions and our future planned tasks, what comes next? Well, that would be further integration. As previously mentioned, we will integrate the transducer fully and incorporate the GUI to automate the system as best as we possibly can. If we make enough progress towards the ABO, eventually we may design a PCB that handles all of the functionality of the current development bench, such as integrating the STM microcontroller with the stepper motor all in one board. We could encounter troubles in the future, however, including issues connecting the software to the hardware and issues interpreting both high voltages and negative voltages coming out of the signal out of the transducer, requiring us to change the voltage tolerances of the circuit, for instance, a voltage divider or a rectifier. To conclude, we would like to mention our key acknowledgements. We would like to give thanks to Matthew Corvais for proposing this project for our team to work on, and of course, we would also like to thank Dr. Hari Sunak for organizing this program and giving students like us the opportunity to work together on real-world problems such as these. We would like to extend special thanks to Patrick Hagarty for his technical support and help with the STM, and Anna Skelly for answering any questions we had and giving us tips while working in the lab on this project. And with that said, we conclude our presentation on our torque measurement project for Zebra Technologies. Thank you very much.